yeah, nobody knows the link. So,
well, except for the audiences.
Yes, right. So I'll admit the other people then.
Wow. Wow.
It's exploding now. Yeah. Some people at the swimming pool.
That's a good background anyway. Are you out in the middle of a park with a big building behind you on a clock on the wall?
Yes.
Yeah, that's always who has the most interesting virtual background. What does it say?
Okay, we'll wait a few more minutes and then we'll get started.
My background is nothing. Someone's 1,000 feet in the air looking at the lake.
Yes.
It's me.
People are still streaming in, I see. So let's wait a bit longer. Okay, welcome everybody to, this is already the third talk in the DEGA webinar series from the IEEE Signal Processing Society. So today it's my pleasure to introduce Michael Schaub from RWTH Aachen University. So Michael studied at ETH Zurich, and then he got his MSc degree in biomedical engineering from the Imperial College in London. Also at the Imperial College, but then in the mathematics department, he got his PhD. That was back in 2014. And then he did a postdoc at Université Catholique de Louvain, as well as University of Namur. Those are in Belgium. And he also had he was a postdoctoral research associate at MIT. And he was also Marie Curie Fellow. There was also both at MIT and University of Oxford. And after all these excursions, he moved to RWTH Aachen. That was only recently in June 2020. So Michael is an expert in higher order graphs. And so we're very happy that he could present his latest results on this area to us here in the webinar series. So if you have any questions, put them in the chat, and then we can deal with them after the presentation. Unless you have something very urgent, or maybe there's something wrong with the link, then let us know. You can just then unmute yourself and ask the question. So thank you, Michael. So go ahead.
Thank you, Gert, for the kind introduction. Thank you for the invitation. It's, of course, great to speak here. Would be even nicer if this would be in real. But of course, then I guess, you know, not so many people from all over the world could join in. So I hope you can see now the correct part of my screen.
Yes.
Yeah. Okay, so I want to talk about signal processing on graphs and in particular on simplicial complexes. But before going into this, I just want to thank a few of my collaborators that have been part of this. This is Austin Benson from Cornell, with whom I sort of started investigating some of these simplicial complexes ideas back in the day when I was still at MIT. Then we have Mitch Roddenberry and Santiago Segarra from Rice. With both of whom I've been collaborating extensively. Then you should at least recognize one face here. And so, I mean, well, there's Elvin Yusufi and Gert is part of the collaboration as well with the people at TU Delft. There's also Mao Sheng, who is the PhD student there, who I did not find the picture of. And then we have Mustafa Hajiz from Santa Clara in California. So, you know, these are some of the people behind the scenes, and I just want to present a few of the results we've obtained over the last few years. And in some sense, let me start with something rather trivial in some sense and kind of very simplistic, right? So and you'll see, however, that I think this picture that I want to project onto you is sort of what I'll use as a guiding example in some sense throughout this talk. And okay, so let's get into this, right? And it's just about linear filtering. So the most fundamental building block in some sense in a lot of signal processing applications, of course, linear filtering. So we think of the data that we get, some sort of a vector y, let's say it's finite dimensional vector space, and we have a signal S and some noise eta, right? And the name of the game, in some sense, when it comes to linear filtering, is that we want to model the signal and we want to assume that it lives in some kind of linear subspace of Rn. And now we want to do filtering, right? And so how do we do that? Well, essentially, we can think about this in terms of 3 steps, right? We project into some kind of new signal basis that spans this subspace of interest to us. And we'll do this by this sort of V transpose transformation, where V is assumed to be a matrix containing all the basis vectors that we're interested in. Then we modulate certain frequencies, right? And we transform back, and this is our filtering approach. And the classical choice here are Fourier basis, right? But of course, the challenge in some sense, if you want to do signal processing, is you need to have a good model for your signal and a good model for your noise. And if you have that, then well, then you can do interesting filtering operations, right? So the quest is on basically for good signal representations, and the classical example of a complete orthonormal basis, a Fourier basis, is of course, you know, dates back, I don't know, the ancient times. And more recently, well, people have explored wavelets, all sorts of other type of dictionaries, so over-complete dictionaries rather than complete orthonormal basis, sparse dictionaries. And of course, the most recent trend is rather than going to some sort of additive decomposition of the signal in terms of a dictionary, you go for composition of features, for compositions of functions in the form of deep nets, right? And what I want to talk today about is basically, well, how to find good signal representations for signals that do not reside in a regular domain, such as a time, an image, or a video, or something like this, but that signals that reside on a graph and and its high order extensions, in particular in terms of simplicial complexes. But if you cannot take away anything from this talk but this, then it's about, I'll basically present you some useful, what I think are useful basis functions for signals defined on these complexes, and we'll talk about interpretations of these. Okay, let's get into this. Let's just quickly recap signal processing on graphs, which has been a very hot topic and very lively topic over the last decade or so, I would say. And it's a very interesting area where, well, I got interested in during my postdoc as well. And so the question is basically, well, how do we define signal and noise on a graph? And by doing this, how do we define, say, smoothing, interpolation, compression, whatever signal processing operation we want to do on graphs? And the picture here is to have in mind is basically, we have a graph, right? I assume everybody is familiar with this concept, and we attach to every node, we attach a signal. In the simplest incarnation, this could be just a number, but it could be also a vector. It could be more complicated things. And so where do these graphs arise in practice? Well, in a lot of different applications, either because the domain of your signal is discrete to start with. So you could think about signals defined on a social network, maybe the opinion of people, or you can discretize a certain domain, for instance, in the context of computer vision, right? So you form basically meshes, and then you want to have signals, maybe corresponding to some kind of texture that you want to project onto those manifolds, essentially. Okay, so how do we do this? Well, at a very high level, you could say that the idea is really to reinterpret what we typically do in classical signal processing, as I call it here, for regular domains, as doing the same thing on graphs. And what I mean with this, I'll make clear in a second. But basically, the idea is that to say, okay, we did graph signal processing all along without realizing it somehow. I'm exaggerating a little bit here, of course, but so time series, we think of it in some sense as a graph, where graph signal processing, where the graph is just a line, right? So you have every node corresponds to one time point, and you have a data point associated to each node. The same with images. You can argue about the adjacency relationships between the nodes there. Maybe you want to include diagonals as well, but that's fine. It's all going to be a regular domain. And the same for video. I mean, what is video but a sequence of images, right? And so you can stack this up in a tensor. And so graphs and graph signals are the natural generalization of this in some sense. And so now let me explain what I meant with that. Basically, regular domain signal processing is just graph signal processing. Let's just focus on the time series here. And for convenience, I make time wrap around and make the boundary conditions cyclic. So we have a circular graph here where we just enumerate the nodes from 0 to n-1, and we're sort of assuming that this corresponds to time. And we look at the graph Laplacian, which is just a diagonal matrix of degrees, out degrees in this. So it's just an identity matrix, and minus a, where a is the adjacency matrix, right? And now, unsurprisingly, this is a circular graph. So the Laplacian turns out to be circulant. It's a circulant matrix. And what are the eigenvectors of a circulant matrix? Well, they are actually the discrete Fourier modes. So what it means that the eigenvectors of the Laplacians are the standard basis for time series signals, if you want. And it's an interesting basis to work with, right? Actually, it turns out that you can make sort of similar observations for most of these grid-like domains in a very similar way, because they are essentially all, you can think about most of these domains as sort of product spaces, where you basically, the grid is a product of two lines, so you get Fourier modes in 2 dimensions and so on. And so now the twist in graph signal processing is to say, in some sense, that, okay, let's pretend our standard basis vectors to start with were the eigenvectors of the Laplacian. We always did this, and so let's take this now as our basis functions, and let's see what we can do with that, right? And in particular, we're going to say that, okay, the Laplacian is a positive semi-definite matrix, so we have all the eigenvalues are non-negative, and so we can order them, and we'll interpret them as frequencies. So we'll say smooth signals are those that have a dominant contribution from so-called slow eigenmodes of the Laplacian, or in other words, small eigenvalues with small real part. So here's an example, just to get used to this idea, and since we'll also see this again in the context of simplicial complexes, let me dwell on this a little longer, even though most of you have probably seen this. So if we have, let's say, the question of how to interpolate a signal on a graph, we've measured the signal on the nodes V3 and V6, and now we want to basically do an interpolation along the edges of this graph somehow. So what does that mean? It means we sort of want to have a smooth signal as we go along the edges of the graph. And one way to do this is a very simple optimization problem. You just say, okay, let's minimize this objective. The first part is just saying, stay as close as possible to the observed signals, y. And then we have this quadratic regularizer. This is basically enforcing that we use the eigenvectors of the Laplacian to do the smoothing. Okay, to show how this works more specifically in a second, but let's look at the solution. So indeed, it does what I promised. It does an interpolation of that signal along the graph. If you're more from the machine learning literature, this is nothing but semi-supervised learning on graphs, actually. And the solution is a linear filter, right? So that we have the signal y, and we multiply it by some matrix, and that matrix has, because of this structure with the Laplacian in it, has the eigenvectors of the Laplacian as sort of the basis vectors there, right? And so in what sense does this Laplacian actually encode smoothness? So let's look at this quadratic form. And so what are we going to see? Well, we see that the quadratic form is nothing but the sum of the squared differences. So I look at every possible edge. I look at the endpoints of those of this edge, and I take the difference of the signals on the endpoints and I square it up. So it's some sort of like a measure of the variation along every edge. And I would like to say that this is actually the gradient along an edge squared. So the Laplacian is in some sense the gradient squared, which is sort of it's very close to what if you think about it in terms of classical vector calculus. So you should actually say, well, it's the divergence of the gradient. Okay, but when is this cost high? Well, it's high if nodes that are connected have very different values. So the gradient along an edge should be very small. And of course, the minimal cost is if all the signals if the signal is constant, right? So every signal on each node has the same value. And well, this is the perfect smooth signal. It's a constant signal. So this intuition about frequency and smooth signal along the graph is quite natural in there. And indeed, now here's to sort of convey this pictorially once more, the eigenmodes of a toy graph here, as you can see, if you order them according to the eigenvalues going from left to right and increasing smoothness, you'll see that a small eigenvalue means smoother and smoother signals, right? And this just appears, you can also see it from the quadratic form, because if you interpret this as kind of a Rayleigh quotient, you will see that the eigenvectors are kind of the ones that minimize this quadratic form if you subtract the corresponding subspaces there. The main point is, however, eigenvectors of the Laplacian are great as signal representations for signals on the nodes of a graph. That's the main point that I want to convey here. And because we have that, we can now sort of say, okay, let's build linear filters. Let's build them in the standard way as we would do it before. We take the eigenvectors of the Laplacian, we project into that domain. We can use any frequency response, h of lambda, denoted here. and we can amplify, and then we pull back into the graph domain. And of course, if you don't want to specify this in sort of like a non-parametric way in the frequency domain, you can try to approximate this function by a polynomial, and then you can do the same thing in the graph domain. And you might want to do this because this is basically a distributed computation that you can do this by passing messages around in the graph. So it's a sparse matrix vector product that you always get for each multiplication with L. Okay, so so the Laplacian, you can do nice filtering operations with this as well. And indeed, if you're a modern machine learning person nowadays, then you'd say, okay, but this is just linear filtering. What about neural nets? So you can construct graph neural networks basically by taking those linear filters, putting a non-linearity behind it, and stacking them up. So you have a linear filter where you can now adjust these coefficients in there. You put, let's say, a ReLU function just behind it that acts element-wise on the vector, and you call that thing a layer. And now you can stack up a lot of these things into layers, and you can train all of this. And why am I telling you this? Because basically the basic features to start with in each layer, they're still inherited from the Laplacian. And okay, I should say, actually, I've told this story now just with Laplacian because I like it a lot, but you can plug in other shift operators as well, which are basically those that encode the adjacency pattern in the graph, right? In the components of the matrix. And the Laplacian is particularly nice because it's positive semi-definite, but you might prefer let's say, the normalized Laplacian, or maybe you prefer the adjacency matrix or something like this. But I'll focus on the Laplacian because it naturally extends to simplicial complexes. So before going into simplicial complexes, because this is a little bit scary, right? So let's just talk about graphs a little longer for a second, but now let's shift perspective. Let's shift perspective and let's talk about signal processing on graph edges. So the question is now very innocent, right? So what if instead of having the signals defined on the nodes, we have the signals defined on the edges? And why would we want to have this? Well, I think in a number of situations, it's fairly natural. It's fairly natural to have a flow of mass, energy, information, cars, goods, what have you. And you think of them as flows on the edges of graphs, right? And the question that we had back then was basically, okay, this is nice, but so what? Can we not just use the standard graph signal processing toolkit, right? Toolset. And well, the answer is going to be not always, and sometimes really no. And that's what the rest of the talk is going to be about now. Okay, so let's start with an idea of how we could actually try to make graph signal processing work if we have the signals defined on the edges. And you could use a very simple idea, which is the so-called line graph transformation, or sometimes this is called the dual graph as well. So what's the line graph? So we start with a graph G, and we construct a new line graph, GLG, where each of the edges in the original graph become a node in the line graph. And these nodes in the line graph are connected if the edges in the original graph shared an endpoint, shared a node, right? So let's say edge A is connected to edge E because it shares node 4 as an endpoint, right? And so by doing this, we have now a new graph where every edge is a node. And since we said before, well, we have now signals associated to the edges, we have signals associated to the nodes of the line graph. And there you go, we're in graph signal processing land again, standard graph signal processing land. So we could just process those signals using the standard toolbox that we've developed. Okay, so now let's try to do that. Okay, so we're considering here a flow, and this is important in the following. So we have a signal that's a flow, and then make it a conservative flow. This is a nice little toy example here. So everything that goes into a node comes out, right? So we have flow conservation. Now I'm going to add a little noise everywhere. So this looks a bit jumbled up. Okay, not perfectly conservative anymore. But now I want to say, okay, I just want to estimate the original F0. So for instance, I want to do a low pass filtering of this, right? Okay, so I'm gonna do this as follows. I'll do the line graph transformation. I associate each of the signals to the nodes of the line graph, and apply my Laplacian filters. And turns out that actually things get worse. So our initial error of 3.8 is now 6.6. So something wrong is going on here, right? And I want to emphasize here that, okay, I've used a specific functional form of the filter here, but you could also use an infinite impulse response filter, or you could do other things as well. The crux is really that somehow this line graph transformation is not what we want to do here. And let me try to explain a little bit why this is the case. Okay, so what we said before is that the Laplacian will penalize signals that are adjacent and very different, right? So we don't want that. We want to have signals, if they are adjacent, they should be very close. So in essence, what you're doing is, if you do this Laplacian filtering, you're essentially doing some kind of distributed averaging. You're averaging over your neighbors in some sense. So you want to stay close to the signals of your neighbors. Now in the line graph transformation, that means that the signals that are on the edges, if they're adjacent edges now, they should be close, right? They should be close to each other. And you can see that the line graph filter actually does that, right? It makes all the edges relatively close in value, sort of around 5. But now here's the problem, right? So this has nothing to do with flow conservation or anything. In fact, it would be perfectly normal if you had the condition on the first, right? Where you have like a flow of 9 going into one edge, and then 6 goes to the right and 3 continues, right? If you sort of cars going into a crossing, I mean, some go right and some go straight. That's perfectly fine. There's nothing strange going on, right? So we want another filtering operator here. We don't want the Laplacian of the line graph. That's what I'm arguing for. So basically what I said is that the notion of smoothness on the graph is not really adapted to this flow-like data that I've shown you. So we want to have an operator somehow that encodes the cyclic structure of the graph, or let us encode this sort of idea of the divergence. And so, okay, how can we do this? Well, we use the so-called Hodge Laplacian. Okay, so let me parse this for you. So in the first instance, we actually didn't use the general Hodge Laplacian. So let's just focus on the edge Laplacian for a second. If the standard graph Laplacian is B transpose, where B is the incidence matrix of a graph, I've just plotted one here for you for the specific toy graph, right? So every edge, you assign an orientation, and you say, for instance, I'll have this edge CE. It goes from C to E, so you put a -1 here and a 1 here. And L0 is B transpose, and L1 is just flipping things around. And there's a more general version of this. This is the so-called Hodge Laplacian, which I'll get to slightly later, where you can also have filled-in faces. So this is more like a hypergraph. But let's focus on the edge Laplacian for a second, and let's look at some of the nice properties that it has. In particular, this operator, rather than Laplacian, where the null space is associated to connected components, the null space is associated to the cycle space of the graph. So every vector that's in the kernel of the L1 Laplacian here is a cyclic flow. And orthogonal to this is the space of gradient flows. And this is just the image of B transpose. Okay, so okay, let's keep that in mind for a second, but let's just zoom out and go for the general Hodge Laplacian, because the general theme I'm going to advocate for here is that basically almost 0 eigenmodes of any Laplacian are to be understood as smooth signals. And the eigenvalues of these Laplacians correspond to frequencies in a natural way. All of these Laplacians are positive semi-definite, so we always have a natural ordering, and they're always symmetric as well. And now this Hodge decomposition for flows, the general one, actually has a natural analog in vector calculus. So in vector calculus, you learn that every vector field can be decomposed into three components, into a set of gradient flows. That is to say, I associate a scalar value, a potential, to every point in space, and then I look at the gradient of this potential, and it gives me a flow. These are the gradient flows. And then if you're an engineer like me or by training, you never hear about harmonic flows, you only hear about curls. So let's go for the curl. Well, the curl is that what you get if you have a magnetic field that's changing and so on, right? So these are locally circular flows that you can contract to a point. So if you do Maxwell equations, you'll see a lot of these curl flows. And now this thing in the middle, the harmonic flow, it only exists in non-Euclidean space. And while actually we're concerned with this here, so it appears in our case. And in the continuum, it means basically, okay, let's say you have a flow in the sphere. So let's say it's sort of like some ocean current, right? So now if you had a flow that goes around the equator, this is not a curl flow because it's a globally cyclic flow that's sort of not that's not local in a sense. It doesn't look like a curl, but it's also not a gradient, even though locally it might look like a gradient. So this is the other exception here. And this Hodge decomposition is really at the core of the interpretation of this basis function of these Hodge Laplacians that we have. Okay, so now this was quite a bit of talking. Let's see some pictures. So here I'm showing you the Hodge decomposition as a signal basis for the edge Laplacian. It's the same toy graph that we had, but now I have 8 eigenvectors corresponding to basically they span the space of all possible edge flows. On top of that, you again have the eigenvalues of this, they're ordered. So now we have 2 eigenvalues of zeros, and lo and behold, they span the so-called cycle space. You can see there are cyclic flows here, one corresponding to this triangle on top, and the other one corresponding to the sort of little 4-node motif at the bottom, right? And they are conservative flows. Everything that goes into a node comes out. And so now, the more you go to the left, the more you will see that you have a divergence, or like you're deviating from flow conservation. That is, not everything that goes into a node comes out. In fact, some nodes have an accumulation of flow and others are losing constantly flow, right? And this is the space of gradient flows there. And the more you go to the left, the more of a gradient you have, more of a gradient flow you have, okay? So now that we've learned this, let's use it. Let's plug this Laplacian in instead and do our flow filtering. And because we have the cycle space in the kernel, right, what we're going to do now is, well, we're going to promote cyclic flows. We basically take the noisy signal, we project it roughly speaking, we project it onto the cycle space. We keep some of the other components because it's not a perfect low-pass filter here. But this is essentially promoting cyclic flows. And you can now see that really we have this right-hand side flow here, which is sort of on the order of 6, and we combine it with sort of on the order of 2.5, let's say, on the left-hand side. And these two flows, these two cyclic flows, they are orthogonal in the space of, well, they're not orthogonal in the space of flows, but we can span the flows that we see here by those two kind of flows. Okay, so that's what I want to say. And of course, it leads to a actual decrease in the error. So this works, right? And the reason is fundamentally we have now the right representation of our signal at the back. We have chosen the right signal representation. Okay, so we can play this similar game in other contexts. Now we want to look at semi-supervised learning, and so the setup is as follows. We still are not in the world of real simplicial complexes as well, even though graphs are actually also simplicial complexes. So we kind of are, but not in the most general setup. So now we've measured only a few edges, and our problem is more akin to sort of a matrix completion problem or a semi-supervised learning problem again. So we want to infer the remaining flows on the graph. And what we're gonna assume here is that we have, again, some kind of flow conservation. So what we now want to penalize in our objective is basically if we diverge from flow conservation, or if we have a divergence. And this you can perfectly express in this way with a quadratic form with the edge Laplacian appearing in it rather than the node Laplacian. So now we allow also for side information. We may have some side information. We say, okay, there's a particular sink here. I don't know, this is a particular urban area where a lot of people go to in the morning. So it's like downtown or something like this. So we allow for some node potentials, and on those places we can basically deviate from flow conservation without too strong of a consequence. And then we end up with the following problem to solve. So the first part is, again, essentially the same as we had in the node case. We want to stay as close as possible to the measurements. Then we have a second part, which basically is we want to penalize divergences, or we want to penalize basically deviation from flow conservation apart from the places where we have some sources and sinks that we might want to put in a priori. This could be 0, right? So you might not have any information. And then we need this extra term here because, well, in general, this could be still an ill-defined optimization problem because the edge Laplacian can have a lot of 0 eigenvalues. And so, for instance, if we have no measurement at all at a particular cycle, we could just add whatever cyclic flow on top of that circle, and it would not lead to any cost in this term. And so in this term here, right? And so it would be not uniquely defined, the optimization problem. So we add a little regularizer that basically ensures that, yeah, we try to get sparse flows in 2 norm, okay? So does that work? Well, yes, it works quite well, actually. This is some real traffic flows and real networks in Anaheim and Winnipeg. And if you can see it below, so this was submitted to computer science conferences, and in computer science, if you want to be a bit tongue-in-cheek, sort of, right? So if my line is above your line, I win. And clearly, flow SSL, as it's called here, beats the line graph approach, and it beats some other approaches as well, in the sense that we need far fewer labeled edges to get a very close correlation to the ground truth flows. And yeah, it's nice to see that these ideas work. So what have I told you so far? Let's just make a brief recap for a moment. And basically, I've told you that, okay, just think of signal processing on graphs and complexes as a simple generalization of classical signal processing, where you plug in the eigenvectors of the graph Laplacian as your favorite signal representations, as your favorite basis functions. And now the Hodge decomposition gives us actually a nice way to interpret these flows. Basically, we have these gradient flows, we have the harmonic flows, and we have curl flows. And we can naturally encode this idea of flow conservation in the harmonics of that Laplacian. However, this idea of a simplicial complex hasn't appeared yet, because for a simplicial complex in a general setup, you need something that's called phases. And the question is, what are those things? And can we do more if we include this kind of information? So now on to signal processing on complexes with phases included. So what is an abstract simplicial complex? That's the question to answer first. So a graph is a simplicial complex that just has 0 simplices or nodes and 1 simplices or edges. And now for a simplicial complex, you simply allow simplices of high order. So you have filled triangles, that is sort of non-empty triangles. There's an area, you can paint them in, and you have 3 simplices and 4 simplices and so on. But for the purpose of this talk, actually, we just need to have 0, 1, and 2 simplices because that's all we're going to need. Okay, but you can extend this to the general case. So now here's the Hodge Laplacian again that I showed you, and it's built on two kinds of incidence matrix. The first kind is the boundary matrix or the node to edge incidence matrix that you all know from graph theory. So it encodes, basically I have an edge, I give every edge a reference orientation, and I say, okay, I put a -1 at the source and I put a +1 at the sink of that edge. And this is how I defined an orientation. Note this is it's a matter of bookkeeping. You can think of like B for bookkeeping matrices, right? And I only want to say that, okay, if I go, let's say, with the arrow here, with the orientation, I want to count this as a positive flow. And if I go against it, I want to count it as a negative flow. So I want to have a notion of orientation associated to each of the edges. And by the same idea, I also assign an orientation to each of the triangles. And you can do this in a clockwise or counterclockwise way. And now I have a second set of incidence matrices, and these are the edge to triangle incidence matrix, if you want. And basically they say, if my edge has the same reference orientation or is aligned with the reference orientation on the triangle, then I put a +1, and otherwise I put a -1. And you can see an example of such an edge to triangle matrix here. Unfortunately, there's a little typo here. This should be edges, right? So this should be AB, BC, and so on, right? So let's say this edge, right? You put a let's say it's this edge, right? This edge you put a 1. This edge you put a 1 because it's oriented, and this edge, right? It goes against the reference orientation, so you put a -1, okay? And now you basically can build this Hodge Laplacian. It's just one matrix that maps from edges to edges. And okay, what does that do? What does it help us now to have this? So the main thing that we can do now by having this filled in triangles is we can now distinguish two different kinds of flows. Before we said the edge Laplacian, all cyclic flows were actually in the kernel. Now we have two sets of flows, cyclic flows that we can distinguish. The curl flows are those in the discrete now that I can create by basically putting together a lot of these triangular flows that go around every triangle. One way to think about it is you associate to each triangle, to each filled triangle, a number. And that number gives you a circulation around that triangle. And every flow that I can create by a linear combination of those triangular flows is a curl flow. And every flow that I cannot create in this way is a harmonic flow. And in here, I just put a little hexagon into the places where I have a hole in that space, meaning that this is not a filled polygon here. And clearly, this flow, this circular flow, I cannot create with such a curl procedure because there is no triangle to start with. Right? So, however, this little picture here below is a little bit deceiving in that harmonic flows are in general globally supported. And so to get there, let's look at another example. So from now on, I'm just going to always fill in all the triangles. And so all these things are considered to be filled triangles, but I have two holes in that space and they're empty. And that means also that the dimension of my harmonic flow, the dimension of the kernel of the Hodge Laplacian is two-dimensional. And I just have this simplicial complex here. So think about it as a discretization of some space. And I put some flow here, and the flow is basically, roughly speaking, it's going from this top left to the lower right here, okay? This is just an example. And so now let's look at the harmonic flows associated to that space. And as I said, for each of the holes, you get one harmonic flow. And now you see that these are quite global supported, but roughly speaking, we have one harmonic flow here that goes counterclockwise around the lower left hole, and you have one that goes clockwise around the upper right hole. And so, and I want to use this harmonic flows now as some kind of a feature map, right? So this is now this is now the ones that I want to focus on. These are the signals that I consider to be important. And what it means is that, let's say, if you have a projection onto this harmonic flow, right, it means that, let's say you're a single edge, right? It means you're aligned with this harmonic. And in particular, if you're closer to that hole, you have a stronger projection. If you're far away, less so. So the simplest thing that we thought, okay, well, let's start doing something here. And we thought about diffusion maps, which is this idea of projecting onto the eigenvectors of the graph Laplacian, the node indicator vectors. So we started with the edge indicator vectors. So we took those flows that we have here, and we just projected them onto the corresponding harmonics. So it's just a single edge with a single number here. And you can see how this looks like. And you think like, okay, well, that's probably not so interesting. However, you can see already some patterns. In general, the trend was that the flow was sort of going from the top left to the lower right. And in the middle part, it goes against the harmonic, right? Against both of these harmonics as well, in fact. And here it goes with this harmonic. And if you go around here, it also goes with this harmonic. So somehow it tells you how aligned a single edge is with respect to the harmonic flows. So this is how it looks like if you just project it. Most of them are fairly small, close to zero, but you get a little bit of signal out of every edge. And when is this actually way more useful? Well, it's way more useful actually if you think now about trajectories, if you think about flows on those, on this simplicial complex. So we have like 3 archetypical types of flows. And how do we encode such a trajectory? Well, we basically just build an indicator vector. So we say, if my trajectory includes that edge in the right orientation, then I put a +1. If it includes that edge in the opposite orientation, I put a -1, and I put 0 for all the others. So it's a very sparse edge indicator vector. And now I project it onto these harmonics. And what do I get? I get this embedding here. I get this representation. And interestingly, right, so now this basically tells me how these trajectories behave topologically with respect to these holes. Each hole has a harmonic function associated to it. If we project onto this, I basically tell you, okay, how much aligned I am with this harmonic flow with the first one. Remember, this was going counterclockwise around the lower left hole. So you see a positive projection on this of this red, green, and orange trajectories here. And it basically has nothing to do with the second hole because that was relatively far away. And if anything, it's slightly negative, right? And so now you can clearly distinguish these 3 types of trajectories with a very, very low dimensional representation. So in principle, these trajectories can be very high dimensional objects, very complex spaces, but we can sort of track their topological behaviors just by looking at this harmonic projection. And we think this is kind of nice. But what about real data? So let's look at some real data. Now we have trajectories on the ocean. These are buoys that drift in the ocean. And this is fairly noisy data. These buoys lose contact with their satellite link and whatnot. And so our question was, nonetheless, can we derive some low dimensional representation? I mean, I'm not an oceanographer, so I'm not inherently interested in these buoys, but we wanted to apply this to real data. So this is Madagascar, which you all realized, of course, and so now you have all these trajectories. Here are buoys that arrive in Madagascar from the east, and they either go south around the island or they go north. And so we were wondering, okay, can we find a low dimensional representation of this and sort of classify this trajectory somehow maybe? So what we did is we discretized the space. We just choose a hexagonal grid because then we get a triangular lattice and we can fill a lot of these triangles. So basically each hexagon becomes a node. We link we link 2 nodes if there are a sufficient number of trajectories going through 2 adjacent hexagons, and we fill the triangle if there's a sufficient number of trajectories going through that area as well. So this is how we define the faces, and now we can do the same thing. We basically discretize the trajectories as well, Now we have them as edge vectors, and we can project them onto the harmonic space that we created from this. Okay, and this is how it looks. And so you can clearly see that, well, there was one hole in that space that corresponds to Madagascar. Buoys tend to not go through land. So there is a harmonic flow here. And indeed, we can see that there are some buoys that sort of go counterclockwise and others that go anti-clockwise. They go south, right? And the second harmonic flow is actually interesting because in some sense, it's data-driven. Well, it's data-driven because of the choice. We said we don't put a filled triangle if there's not enough, if there are not enough trajectories going through this. So these are rare trajectories in some sense that encircle this little hole here, and it's sort of like a local vortex-like flow that you had at the southwest tip of Madagascar. And actually, we used this idea in some recent follow-up work to do outlier detection, where basically we are then saying, okay, let's say you can actually plant those holes, then it would allow you to distinguish certain classes of trajectories, but I'm not reporting on this here now. Sure, like wrapping up almost, let me just flash a few more other applications. So I've shown you basically low pass filtering essentially and harmonic projections, but you can do the same thing as you do on graphs. You can construct finite impulse response filters. Here is some work with Gert and Mancheng and Elvin that is in USIPCO. And the interesting thing here is that because we have two sets of matrices appearing in the Hodge Laplacian, it makes actually sense to give them different filtering coefficients. You want to be able to tune the curl components and the gradient components individually, and that pays off. And so this is what this is about. But I've basically shown you the equivalent of sort of, a complete orthonormal basis. So Fourier kind of modes on these simplicial complexes. Can you do more? Can you do wavelet-like things? Can you do overcomplete dictionaries? Yes, you can. Basically, you build upon those ideas that people have proposed for graph wavelets, and you can translate this into wavelets on complexes. You can also extend this to more general spaces. I've talked about simplicial complexes here, but you can actually extend this to cell complexes. That means you can basically, well, roughly speaking, you can allow for any polygonal shape, and you can declare this to be a filled area. So you can have, I don't know, not only just triangles, but whatever polygon is your preferred one, hexagons or something like this, right? Okay, so with that, I want to close and want to say, okay, what did I talk about? Basically, I talked about a useful set of basis functions for signals defined on complexes. How did I do this? Well, I mean, basically, the argument was signal processing on graphs and complexes is nothing but a generalization of classical signal processing and the idea of finding the right representation for your signal. The Hodge decomposition for the one Laplacian, or the one Hodge Laplacian, is actually a useful tool for interpretation, and it gives us a nice set of unitary basis signals. I've shown you a few examples. And if you want to know more, you can check out references at my homepage. I want to also add, we are, of course, not the only people in that space. So if you're interested in this kind of work, Sergio Barbarossa, for instance, in Italy, and Stefano Sadelitti, they have done a lot of interesting work here as well. I mean, Santiago and Mitch have a few works also on extending this to graph neural networks. There are some other people, Michael Bronstein et al., they have also gone into this direction. There's work by people at EPFL looking at this. There is work from the group of Marina Mela on so-called Helmholtzian eigenmaps. So there's a lot of interesting stuff, and I would all invite you to look into this, because I think it's very interesting area. But now it's time to close, and thank you for your attention, and looking forward to the questions. Thank you.
Thank you, Michael. Very exciting talk. Very nice. Let's go to the chat first for some questions, maybe. I see there were some questions on construction of the line graph. I think you kind of explained it during your talk. It was also answered in the chat, I see. There was still a question about defining zero crossing points of a line graph I'm not sure what.
Okay, I'm not 100% sure that I understand the question there. Is it basically really you sort of want to geometrically say that two edges cross?
Yeah, if Rugu is online.
Maybe you can send me an email and we can figure this out. I'm happy to. Zero crossing on basis function. I see. I think there is a link.
Okay. Yes. Yes. Okay.
So zero crossing on basis function, I guess you mean that I have degenerate eigenvalues, yeah? So something like this can happen. Basically, the harmonic space, as I've shown you, is degenerate. So you can, choose whatever eigenvectors you want to have. You can rotate them around. And however, for the purpose of filtering, that's just fine because the space is invariant, and that's what we care about. Now, I don't know whether this answers the question, but okay, maybe I can renew my offer. If this was not what was meant, somehow just feel free to get in touch. The difference between the curl and the gradient seems clear. Exactly what is harmonic flow and how is it different from curl flow? Okay, so the harmonic flow, the simple answer is somehow the harmonic flow is everything that is not a gradient or a curl, right? But so the harmonic flow is cyclic, and however, it's cyclic, but you cannot compose it from patching together these local vortex-like flows. So there are basically flows, for instance, like this four-node motif that we had. You cannot get them, and that corresponds to a hole in space. You should think about this as corresponding to a discretization of a continuous space. And if you have a hole, if you have a homology, if you're familiar with topological data analysis, if you have a homology group that's non-trivial, then you will always have this harmonic flow. So think about a donut, a torus, basically. You can have a flow that sort of wraps around and goes around the surface of the torus. You cannot contract it to a point because there's the donut sort of in the way, right? And that's a harmonic flow. I hope that gives you a rough idea about that. Transpose x Lx as a measure of smoothness of a graph signal of x. What if we consider the minimization of the difference between the graph signal and its shifted version with x minus ax in order to obtain a smooth graph signal? So this is related to graph signal processing on the nodes, I suppose. So, I mean, of course, in general, you have lots of different choices to measure variation on the graph. You could do this, although I'm not familiar with.
I think this is often used when you have a directed graph and you have adjacency matrix. So then the Laplacian is not so common.
I see. Well, there you go.
And
it's another way to measure variation, of course. So there are lots of choices, right? It's not that anything that I said is set in stone, and now there's lots of open direction.
Maybe related to that, I had a question like, can you define also some theory related to adjacency matrices in these higher order structures, in these simplicial complexes?
So in principle, yes, you can do. So you can define upper adjacent and lower adjacent adjacency matrices. Well, I mean, we haven't looked at the spectral theory of those matrices, but it can be done. I'm not too familiar if there's a lot of theory out there. So this is a great avenue for some more research, it seems. But I mean, I'm also not claiming that I know everything.
Okay, no, I was just wondering. Okay.
I'm not familiar with anything that goes in this direction. If you are interested in sort of the relation, there's some work by Muhammad and Egerstedt and so on, and they give you also the formulas about how these things fit together with the Laplacians that I presented to you, the upper and lower adjacent ones.
Okay, then let's see. Bastian Seifert had a question.
if you have signals supported on the nodes, edges, and faces, each Laplacian only works in each of these. So can you somehow have interactions between these signals supported? So that's a very interesting question indeed. Basically, I've focused on one space here. And you can, of course, try to enforce some sort of joint smoothness if you want. One caveat there is, because this is sort of like a topological construction, if you apply this boundary operators twice, so if you do, let's say, B1 times B2, you get 0. So you will not have an effect from a triangle signal onto a node. You only have one level up or one level down. If you want to avoid this, you have to shift away. You have to go away from this linear construction of the Hodge Laplacian that I showed you. You can do that, for instance, Santiago and Mitch, they argue for doing this in the context of simplicial neural nets, and then you can get this kind of crosstalk. You can also use other constructions as well. So in fact, I've been also talking with some other people about like thinking about this to have some sort of coherency. So one idea could be, for instance, that you have some information on the nodes, let's say in partial information on edge flows, and you can borrow strength from the node signals to infer some of the edge flows, for instance. That could be a useful idea to explore. Referring to zero crossing of eigenvectors entries as a proxy of graph frequency. Okay. Yeah,
I think that's related to Perugu's.
That's the zero crossing question. Yeah. Okay. Yes, that could be. Shameless plug. Okay, let's advertise the simplicial neural networks that I've referred to. Yeah, exactly. Look this up. Stefana Ebli, Michel Deferrand. It's interesting work there as well. Okay, now Felix has, thank you for the talk. If the edge signal has only a gradient component, does an equivalent node signal exist? For example, if I want to low pass filter an edge signal with only a gradient, could I also filter an? Yes. The answer to this is yes. If you have only a gradient flow, then there is always going to be a set of node potentials that induces this gradient flow. This set of node potential is not unique, however, because you basically can add a constant offset at every node, right? But that's the only non-uniqueness. In fact, you can also share, you can show that basically the eigenvectors of the graph Laplacian, if you apply the appropriate boundary operator, they will sort of morph into gradient flows. So you can choose any eigenvector of the graph Laplacian, plug in the edge to node incidence matrix, and you get an eigenvector of the Hodge Laplacian. And this eigenvector is going to be a gradient flow because it is induced by node potentials. I hope that answers the question.
Okay, does anybody else have a question? Then feel free to unmute and ask the question to Michael if you want. Don't see any hands going up. The question.
How do you define entropy? I don't know what this is. That
I don't think you used it here, right? So
yeah, well,
Wikipedia,
I didn't use it here, but yeah.
Okay, so no questions. I think then we can wrap it up here. So thanks again, Michael, for the nice talk and for answering all the questions in the chat. So yeah, with that, thank you also for the audience for attending. So in 2 weeks we have another talk. So tune in at that time. So we will send information by email. So it's always the same link that you can use, and we will send you reminders on the details of that specific presentation.